In this video, we're going to talk about the different ways that we can test a regression model. And let's get a model up here so we can talk about it. We're going to start with the global f-test, but we want to take a look at this model. This is the example I'll be talking through this entire video. And obviously, as the model changes, the way that we test it will change as well. And let me be careful there. The idea is there's three different tests that we have at our disposal. Those ideas stay the same regardless of what model we're looking at, but the specifics of the test, the null and alternative hypothesis we're specifying, the models that we consider change obviously as the starting point changes. I chose this model specifically because this is your model that you're going to be working with on your projects. It's the complete second order model when you have a quantitative x1 and a qualitative x2 that has two levels. So x1 squared, this was our step 1 of our model building. This is step 2 and this is step 3 where you put in the quantitative terms, then you add the qualitative terms, and then you interact both of them. If you have any questions about that, go back and take a look at my video where you're building the complete second order model. So we get a starting point. That's the major point here. We have a starting point. We have a model that we want to consider, and now we want to take a look at how do we test it. Well, I'm going to talk about three tests that we look at. The first one is what I'm going to call the global, and really what we want to ask and answer is, does anything here work? Are any of these independent variables useful at predicting y? Then there's going to be, hopefully we answer yes to that, by the way. Something is useful, that would be a good thing. And then we're going to say, well, if something works, is it this part? And is it this part? Really, there's a couple of ways we have to look at that. If it's a single term, if it's just one of the terms in the model, and so here I would talk about there being two variables, x1 and x2, but 5 terms. If I just want to look at a single term one at a time, or if I want to look at a term, I'm not sure how to say that. If I want to look at a single term, I could do a t-test, and that t-test is going to be very similar to what you guys did when you were looking at simple linear regression. We had a straight line relationship. There was a single beta, a single x variable that we wanted to test. We looked at the beta and we did a t-test, and we could do the same thing if we're testing a single term. But say I want to test a couple terms. Say I want to test, let's say, these back terms here, these two. Let's say, do they work? Are they important? Well, that's testing 2 terms, and whenever you're testing 2 or more, that's called a partial f-test. And there's other names for it, depending where you look, and we'll get into some of those. But that's a partial f-test. If you're testing the whole thing, it's a global. If you're testing a part of it, 2 or more terms, but not all, that's a partial. And if you're testing just a single one, that's a t-test. And so obviously you need to know the model you're working with pretty well. You need to know what it is you're testing or wanting to test, and that'll dictate the type of test you conduct. All right, so here let's start by talking about the global f-test. The global f-test, we want to test the entire model. We want to ask, are any of these terms useful for predicting y? And what you should realize is, if a term is not useful, if you're going to get rid of it, what would the value of beta be? What would the value of beta 1 be if I get rid of this x1? Well, it would be 0. What would the value of beta 2 be if x1 squared wasn't useful? To get rid of it, it'd be 0. In fact, the global f-test specifies all the betas attached to the terms, not beta naught now, right? But all the betas attached to the x's. I don't care which x you're talking about. In a global, you're testing them all. And so you take a look at what your biggest beta is, beta 5 here. And so we're going to say 1, 2, 3, 4, and 5. Now we specify the betas, not the x's, but we're specifying that the betas attached to the x's are all 0. And what the null says in words is that none of the variables, none of the terms are useful for predicting y. Okay, the null says nothing works. What's the alternative say? Well, you've heard me say this before. The alternative always says, nuh-uh. It says the null's not right. Well, how do you say the null's not right? Well, we don't want to say they're all not equal to 0. What we're going to say is at least one is not equal to 0. At least one of the betas. Now, some people go a little crazy and talk about this beta here, and they'll say, oh, it's beta I is equal to 1, 2, 3, 4, 5. I'm just going to write the beta. I'm going to leave the subscripts off. And I just want you to know that the beta, what we refer to here, and I'm going to assume the same thing when you do it, the beta you refer to here is talking about the betas that has been specified in the null. And so we're saying at least one of these guys is not 0. In words, the null says nothing works. The alternative says something works. It's not specifying what, but it's saying something works. And so now we've set up a test a hypothesis. Well, good news for us, if you're surprised by this, wow, where have you been all semester? But if you're surprised by this, there's a test statistic and a p-value that we're going to get from a printout. How do we do that? Well, I'll show you that in another video. I'll show you how to generate the tests, and I'll go through and I'll show you how to generate the test statistic and p-value for the global F, for the partial F, and for the t-tests. But you're going to need to interpret a p-value for me. Here's how we do it. Reject H naught. Something works in the model. When p is low, we can reject that null hypothesis, right? What's that mean here? It means something works in the model. Do you think you're done? No, you got more work to do, my friend. Something works. I'm going to be asking you to go and find it. We're going to be testing different pieces. Okay, so more work. And I know from your seat or from wherever you are, you're thinking, more work. But this is good. We're learning. We're gaining knowledge. We're on the road to predicting Y better. This is a good thing. If P is high and we fail to reject, you would stop. And I know from a student's perspective, you're like, oh, I want that. That would be really good. I'll be done. That'd be really bad. We're not learning anything. We're not gaining any information. This is where I'm going to say to you, for most part, think about when we've been doing test the hypothesis, what alphas have you been testing at? And I think pretty much all semester I've been consistent, right? I said your reliabilities are between 90 and 99%. Flip them around. Your alphas are between 0.01 and 0.10. That's where your alpha should be. But in this case, when you're doing your multiple regression project, you have no alpha restriction at all. If your p-value on your global F test is 0.45, I want you to test at alpha equal 0.46. Everybody on your regression work, on your multiple regression project, you will be rejecting the null here regardless of the alpha you use. It's the only time I will lift my alpha restriction. Any future tests you do after this, your alpha has to be you can't go any higher than 0.10. But for your global F test, this would be the only time all semester I let you break that rule. And that's just so you don't stop. I don't want anyone going to the global F test of their multiple regression project and saying, well, my P was high, so I stop, I'm done. Turn in one printout and say, I'm done with it. Nope, not going to let that happen. So we're going to fake it, we're going to raise our alpha, and we're going to move on. Now, hopefully, you have some data that's going to work. Hopefully, your X's will help predict your Y, and you won't have to cross that bridge. But that's how we do a global F. We test all the terms simultaneously. It's a very efficient test. And hopefully make the conclusion that something works. So what's next? Well, what's next is we're going to test a portion of the model. And so in order to do this, we need our full model. Well, we have the same model from the first page. Okay, and again, as your complete second order model changes, what we call our full model is going to kind of follow along. So there's the full model. Now let's say that I want to test the quadratic portion of the model. Okay, take a look at this model here. What pieces, or which terms, better way of saying it maybe, which terms in this model would you say are the quadratics? Now you got to go back to our model terms talk. What makes a term a quadratic? Well, the squared term. Here's a quadratic term. Here's a quadratic term. And so if we think about it, those would be the quadratic terms I want to test to see. And really the question I'm asking here is, we've included the curves. We've included those terms in the model to allow for a curvilinear relationship between y and x1. But the logical question is, do we need them? Or another way of asking the question, are the curves providing useful information? Is this regression project better off using curves or lines? That's really what we're trying to figure out here. Because if I take the curves out, I still have the linear relationship in there. And so I'm asking, when we do this test, when I test the quadratic portion of the model, I'm asking the question, do I need lines or curves? Okay, now the way we're going to do that is we're going to set up the null hypothesis. The null is going to say those terms we just identified, the quadratic piece that we want to test, the null, by specifying these two betas equal to 0, what's it saying about those things? It's saying the quadratic part doesn't work. It's saying you don't need the quadratics. It's saying take the quadratic pieces out of the model. What's the alternative saying? Well, at least one of those betas, again, you don't see the I there, but you can think about it. At least one of these two betas, the beta 2 or beta 5, is not equal to 0. Well, what's that saying? If you tell me at least one of these betas is not equal to 0, then what you're saying is, hey, I think they work. They're needed. We need to keep the quadratics. Okay, and so here's how I'm going to do it. We're going to propose a reduced model. And look at what that reduced model, you just saw it come up in red, and obviously you're writing that into your notes right now. But look at what it is. It's taking those terms that are in boxes right now, the terms that I'm telling you to test. We want to find out if the quadratics are useful. Let's build a model that has the quadratics in it. And then if I was sitting here live in front of you, I know it doesn't translate in the video, but if I took my thumbs and covered up the beta 5 x1 squared x2 and covered up the beta 2 x1 squared, you know what would be left? The reduced model. And so I have this math brain. I really don't try to run from it anymore. I just accept that that's the way it works. Some of you guys have a math brain. Some of you guys don't have a math brain. Some of you have an accounting brain. Here's how I look at it. Maybe this will make some sense to you. We have a full model. Whenever we're doing one of these tests, we have this full model. And as I look at the reduced model and the null hypothesis, the accounting portion of my brain says all the betas go somewhere. Beta naught, okay, check, that's right here. Beta 1, check, that's right here. Beta 2, oh, that one's down here. That one's one that's getting tested. It doesn't show up in my reduced model. Beta 3, yeah, that's right here. Beta 4 is right here. And beta 5 is also down here. And so I'm kind of taking the full model and I'm saying either we're testing those terms to see if they work, or the remaining terms are what we call the reduced model. We're comparing the full to the reduced. Okay, so how do we do that? Well, we're going to go ahead and get a test statistic and a p-value. We're going to go to the computer, and again, I'll show you how to do that. We're going to go to the computer. In fact, the next slide gives you a little bit of insight into that. And we're going to get the test statistic and the p-value from the printout. And again, when p is low, reject the null. Okay, if our p-value for that printout is low, and tricky to kind of set that up a little bit, but I'll show you how to do it. It's not too difficult. If you reject the null, if you say at least one of these betas is not 0, what are you saying about those terms? Well, at least one of these terms is useful. Hey, the quadratics are useful. Let's keep them. And if you fail to reject, there's insufficient evidence to indicate the quadratic terms are useful. We can't say they work. We're going to get rid of them. We're going to take those quadratic terms out, and we're going to say we don't need them, and we're going to go with the reduced model. And so we're using our test to hypothesis to start with a big model, and initially we start with a complete second order model. We test a term, or terms in this case, to see if they work, and if they do, we keep them, and if they don't, we get rid of them. And now we move on. And so this is helping us to determine what we're going to do with the quadratic piece. What about the interaction piece? And how you approach, let's say it this way, how you approach the interaction piece depends upon which of these models you use. And so let me go and take that off now. If you use the full model, if you said keep the quadratic terms, after you do this test, if you say keep the quadratic terms, what's the interaction portion of this model? Well, those are the interaction terms. But what if you got rid of the quadratic piece? What if you failed to reject and dropped the quadratics out when you did this test? Remember, you can do either one, depends on your p-value. Well, if you use the reduced model, if you say the reduced model is better than the full model, now you only have one interaction term. And so we're going to start with our complete second order model. We're going to do a global F test. And then based upon our, hopefully, reject H naught, we're going to start looking. We're going to start hunting and pecking. We're going to say, hey, but how about those quadratics? We need them? Here's a test you do. And then we say, oh, what about the interaction? First, you got to figure out how many interaction terms do I have after doing the quadratic test, and then figure out how to test. Sometimes testing the interaction test is a partial F test because you got two of them. What's going to change here? Well, it's not going to be beta 2 and beta 5 are equal to 0. It would be beta 4 and beta 5. The reduced model changes as the null changes, and you would repeat. You're going to change things up a little bit, but you're going to do basically the same thing. Now, others are going to say, hey, I got rid of the interaction terms. I said the reduced model was better. Well, now you just have a single term. How do we test a single term? That's not a partial f-test, because a partial f-test is 2 or more terms. That's a t-test. Hang in there. We'll get there. Okay, this is the partial f-test. Now look what I say about the partial f-test here. Compares two models, one that has the terms in it and one that drops them out, to determine which model is better at predicting y. We call them a full and a reduced model. In statistics, the partial f-test is referred to as the best subset regressions test. Again, I'll show you how to go through the testing when we get there, but here are some instructions that are going to be helpful for you. The model terms are separated into two classifications. And the model terms I'm referring to here, I'm referring to the x1, x1 squared, x2, x1, x2, x1 squared, x2. I'm referring to the independent terms. Remember when I said we have our full model and it gets kind of partitioned into either the reduced model or the null hypothesis? The terms that we're testing. So we say beta 2 and beta 5. That last test we looked at, beta 2 and beta 5 are equal to 0. And so in the program, and again, well, I'll give you an example in a second. I'll take you there. Or I shouldn't say in a second. In another video, I'll take you there. But we would put the x1 squared and the x1 squared x2. Those are the terms we're testing. I'd call them non-forced. And then the reduced model, the x1, the x2, the x1, x2, I'd put that in as the forced terms. And we would look at the printout. There's a p-value on that printout, and that's what we're going to use to make our decision. That's the partial s-test, or the best subset. I'll use both those terms interchangeably. Best subset, the only time I've ever actually seen that used in the software is with the statistics program that we're working with. Typically we refer to them as a partial f-test. Either works. All right, so then we talk about the last test, the t-test. And that tests a single term. And so the scenario that gets you here is, let's say we did that interaction test. I'm sorry, not the interaction test. We want to do that now. Let's say we did that quadratic test. Remember, beta 2 and beta 5 are equal to 0. And the way that I would get to this model is if we failed to reject. There's insufficient evidence to indicate that quadratics work. We can't say they work, so we drop them out. And so in that slide where we had the testing the model of the partial f-test, let's say we made the conclusion that the reduced model was better, and then say, let's go, and now let's test the interaction component. Well, there's only one term that's an interaction component. There's only one piece that's an interaction. And so how do we test that? We do a t-test. Beta 4 is equal to 0 says that term doesn't work. Now, I can still think of it in terms of a full and a reduced model. That idea that I brought up on that last slide that talked about the partial f-test or the best subset test, it works here too. I'm comparing the model that has interaction in it, and now think about putting your thumb over that interaction term, that box term right there. I'm comparing the model that has interaction in it to the one that doesn't. Which one's better? Do I need, and remember we talked about interaction, bringing in non-parallel. Do I need non-parallel lines, or do parallel lines work better with my data set? If I don't need non-parallel, I'm going to get rid of the interaction. If I need non-parallel, I'm going to keep the interaction. How do I know? We're going to do our test hypothesis thing. We're going to generate a test statistic, and again, a p-value, and take a look. And you can see what I'm saying here, a p-value. When we work with t-tests, the p-values we get are two-tailed. Now, when you're testing an interaction term, I think a two-tailed test is in order because it's very difficult to know the direction of the interaction. That's weird. But we will run into some t-tests, or I should say it this way, you may run into some t-tests where a one-tailed test. What if you were testing, what if you got rid of all this piece here and you were testing to see whether x1 is a useful predictor of y? Well, depending on your data, if you're working with automobiles and x1 is the mileage of the vehicle and y is the price, you'd expect the prices to go down as the mileages go up. If you're working with homes and you're trying to predict the sales price based on the square footage, you'd expect the price to go up as the size went up. And so sometimes we know the direction of the t-test, sometimes we don't. The point is, if we have a one-tailed test, the printout's always going to give two-tailed t-test p-values. Wow, that's a mouthful. The printout always gives two-tailed t-value p-values. Wow, it's still a lot. The p-values for the t-tests are always two-tailed. That's better. The p-values for the t-tests are always two-tailed. our test that we want to conduct may not be. And so we've seen this before. You need to adjust the p-value sometimes. And then we make our conclusion. Either reject, in which case we're going to, and just in general, just in model building in general, when you're doing a test, whether it's a global F-test, a partial F-test, or a t-test, if you reject, something works. Whatever it is you tested is working. Keep it. If you fail to reject, drop it. If you reject, there's sufficient evidence to indicate that term or those terms are useful. Keep them. If you fail to reject, there's insufficient evidence to indicate that stuff works. Get rid of it. Build down to a smaller model. And so our whole model building idea is we start with the complete second order model. We test to see if anything works, and then we start chunking it up and test this chunk here, and then we test that chunk there, and then we test this piece here, and then we test that one over there, and we're building down to our best model. And so those are the 3 tests you have to be comfortable with. Now, there's a game plan video that puts it all together, but I'll warn you, the game plan, it's an interesting idea. Some of you will pick it up right away. Others are going to look at it and want to run and hide. I'll try to make it easy for you. I'll try to make it work, but a lot of times what you need to do is just kind of hang in there. All right, before I get to that video, model testing in statistics. Here's how you do it. Now, this is a great little sheet of notes to have when you go to the software and start testing in your model. I know everybody's going to do this once. One check mark. You're going to go to statistics menu, linear models, linear regression. You're going to fit the model that you want and use the F-test p-value. I'll show you where that is in a little bit. And again, I'm going to do a separate video for the statistics demonstration. I use different software for that. For the partial F-test, when you test your quadratic terms in your project for me, again, I'm talking about your multiple regression projects here. You're going to go statistics, linear models, best subsets. The terms to be tested are the non-forced. I know everyone's going to be doing a quadratics test. So your quadratic, at least the first time, maybe the only time, I'll talk about that in a second, when you do the quadratics test, your x1 squared, your x1 squared x2 term, those are going to be your non-forced. Everything else, the x1, the x2, the x1, x2 goes in reduced model. You're going to get a p-value. Some of you are going to say, hey, we need those quadratic terms, keep them. Some of you are going to say, we don't need those quadratic terms, get rid of them. Now, depending what you say there, if you keep the quadratic terms, we're going to do this. Some of you will have a second partial test when you test the interaction because you have 2 of them. If you get rid of the quadratic terms, you only have 1 interaction test and you're going to be down here. And then after that, all bets are off. Depending what you do next, I shouldn't say that. What you do next depends upon the decisions you make on your quadratics and your interaction. But that's a more complicated question and answer than I can do in this particular video. And so what I wanted to do here, my goal of this video was to introduce you to the 3 different types of tests. The quadratics, nope, that's not right. The global, that's right. The partial, and the t-test. So hopefully that's been done. Now, we want to take a look at how we do that in statistics, and then we'll take a look at the game plan. Hopefully this isn't swirling too much. The beauty of videos is, if it is, you can go back to the beginning and watch it again, which some of you right now are thinking, that's the last thing I want to do. So probably a good idea right now is go grab a bite to eat, take a break, catch a nap, change your mind, just put it on something else for a while. But whenever I always say in statistics, one of the best things you can do in statistics is you reach that point where you just want to walk away, or you have to walk away. You're at your maximum. You can't take any more. Walk away. But I always say this, and I'm fine with that. Walk away. But the only way I'll say to walk away is if you promise to come back. Not 3 years from now, but take a break, take some time off. Maybe it's just a couple hours. Maybe it's come back tomorrow, but come back to it, especially if you're struggling with it. Staying away from it for a long period of time is not going to help you if you're struggling with it. The key is to come back to it. And if come back to it includes getting in touch with us and asking questions or posting something on a discussion board and getting your answers, then by all means do it. But walk towards it instead of away from it. Anyway, we're here to help. Get to work.